This is problem 615, and this is a frame, and we like to find the forces at FD. This is this link over here, and DF. Those are two weightless links. So if we analyze our structure, we have, this is a multi-load member, this is also a multi-load member, and this is also a multi-load member. And then we have two, let me write it right here, these are two force members, or it's the same weightless links that only carry load in the actual direction. So to solve this, I will draw the free body diagrams of my three different, of all my components. In this case, I will draw the free body diagram of this member, of this member, to try to find those two. So let's draw the free body diagram. Free body diagram of member GE. I will name it GE because that's only one. Never cut the member when it has a pin over here, for example, at F, because you will find internal forces, not the forces of the pins. So if we draw this free body diagram, right, of G, E, and there here we have a F, we have a pin at F, we have the external force, which is 6 kilonewtons. We have the force that is my tension of the force. I will assume that to be in tension, even though maybe give me probably it's in compression, right? Because I am pushing that in this direction. So I can actually either assume that it's in tension, which will be this case, or assume that, remember when we were solving trusses, we always assume the weightless links to be in tension, and then a negative value will mean that it's in compression. So if I put my arrow in this direction, I am assuming that this weightless link is in tension, which obviously will be in compression because I'm pushing this whole truss whole structure to be in this direction. Okay, so then I have my reactions at E. At E, I will have EY and EX. Those reactions are the ones that, if I leave the pin over here, it means that those are the reactions that this bar does with the other bar, right? Okay, so that's my free body diagram. I will do the free body diagrams of all the elements, and then I will do my calculations. So here I have the other free body diagram, that's from E. I will then draw these reactions because of the third law, Newton's law. It says that action and reaction. I will draw them in the opposite direction. Then I have a D. Since I drew that force, which I'll call FD, I draw in this direction. Here I have to draw exactly the same force. So as I said, I am assuming it to be in tension. And then I will draw, since they are asking me the reactions at the pin C with a C, I will draw this without pin, and the reactions that I will get here are the pin with the bar. So I will get here CX and CY. And I will make it very clear that those are internal reactions. So I'd like to make sure we understand where we are, when we have a pin. This is a three-dimensional drawing of my pin, and as you see, I have this member right here that will be the member that goes up. Then I have the member that goes to one side, So the internal reactions may be actually different. And in this case, I have a third element, which is that wheel that is with the floor. So this is a 3D drawing of pin C. Of course, I always draw the pin in 2D, right? So when I see the pin looking at this side, I just see what I see here, that everything is together, right? But what I'm trying to say is that when I have two elements like in pin E, the reactions will be the same. But when I have three elements, sometimes those reactions don't have to be equal. So in this case, the X could be equal, but the Y could be affected by that roller that I have here. So that's why I call them CX prime and CXY prime, because those are the forces that this bar over here produces with the pin. And then I have the third one that I will draw also without a pin, and I will actually say that these are actually also CY, but I will call it 2 prime. So I will call them 2 prime in the sense that those are different reactions. They probably give me the same but in opposite direction. For example, in CX and CX prime, because I don't have anything else in X that will change those reactions. So those ones will be equals and in opposite direction. But I just, since they are asking me to calculate those reactions internally, I will name them differently. And then I have, I forgot this one over here, which is dB, and therefore I will write right here dB. And finally, I will draw the reactions in A. I can draw that with the wheel, and I will have just one reaction, that is the normal force in A. You see that if I don't take out the wheel, the reactions with the pin will become internal reactions. So those are my three free body diagrams, and then I will add forces in each of them to find the values, right? So the first equation that I will apply, they ask me to find the reaction in FD. So I will apply I will find that one first. Therefore, I will take moment at E. So when I take moment at E, this angle over here is known because this distance is 1. So if we analyze, let me analyze that triangle over here. This is 1, this is 2, therefore this is 1 plus 4, which is square root of 5, right? So this angle is named theta. The cosine of theta will be 1 over square root of 5, and the sine of theta will be equals to 2 square root of 5. Okay, having said that, so I will decompose my force in X and Y to be able to take the moment. So I will see that the whole distance is 3 times 6, and that's a positive moment, plus another positive moment will be equals to 1, and the force FD in the Y component. So I said this angle is theta, therefore I will multiply by sine of theta, which is 2 over square root of 5. That's equals to 0. And then here we can solve for that force, right? And obviously I already know that it will give me a negative value. And that negative value is, so I can say this is 9, this is 18 divided by 2 is 9. So it will be 9 square root of 5. And that force is equals in kilonewtons. That's equals to, I got the value right here, 20.1 kilonewtons. So I was able to find the first. So I know that this weightless link right here is in compression, which makes sense because I am pulling point G. here I have 1, 2, 3, 4, 5, 6 unknown. So in order to use this free body diagram, I will find these two reactions. So to do that, I will add forces in X, and then I have EX plus FD cosine of theta, and cosine is 1 over square root of 5 is equals to 0. So EX is equals to negative 9 times square root of 5 divided by square root of 5. So therefore EX is equals to 9. And then I add forces in Y. I'm still in this free body diagram, right? I got forces in Y. I have negative 6, negative FD sine of theta, which is square root of 2 over 5, plus EY equals to 0. From here, EY will be equals to 6 plus minus, right, 9 square root of 5 times 2 over 5. That means that AY is equals to 18 minus 6 is 12 kilonewtons. So it means that I assume that to be to the right, and it's positive, so it gives me to the right. I assume that to be up, and it gives me a negative value, so it means that goes down. Good. So those are the equations of equilibrium to the first free body diagram, and I was able to find those two. And I have this one too. So now that I found those three, right, I am able to apply my equations of equilibrium to this free body diagram because I have only 3 unknowns. So let's do that. And what I'm going to do first is take moment at C. Therefore, I will cancel these 2 unknowns, and I will be able to find DB because I know the other 3. So let me, for this free body diagram, let me add moment at C, which is equals to 0. So very important, this is 1 and this is 1. Therefore, this angle right here is the same as this one. It's 45 degrees. Good. So let me take moment at C. This one produces a moment, the horizontal component, and is positive, dB square root of 2 over 2, and the distance is 1. This one as well. So let's me FD, and remember that this angle is already known, right? We found our angle, and it's the same as this angle, right? So I can say that is cosine, and the cosine of that angle is 1 square root of 5, and the distance is again 1, right? And it's also positive. And then I have positive the whole distance, which is 3, times E sub x, which is 9, is equals to 0. So from here, I can solve for dB. And I have the value right here. Well, this is easy. We plug in the 9 square root of 5 over here with the negative value. Be careful with that. And then we solve for that. And we get that this is 18 square root of 2 kilonewtons, which is equals to 25.5 kilonewtons, which is also in compression. Okay, so now that we have this value, so we were able to find also this value. Now we add forces in X, and we get Cx prime minus dB square root of 2 over 2 minus FD, and the cosine is 1 over square root of 5 minus EX equals to 0. So from here we are able to find Cx prime, and Cx prime gives me negative 18 kilonewtons. It means that it goes in this direction. And I add forces in Y, and I get C prime y plus Fd 2 over square root of 5 and minus dB square root of 2 over 2 minus Ey. So be careful, you have to plug in the negative 12 over here, you have to plug the negative 9 square root of 5 over here, and you have to plug in the negative 18 the square root of 2. But we learn how to work with negative numbers since high school, right? So don't get confused. That's very important that you know how to manage negative numbers, right? So, and C prime gives me 12 kilonewtons, and it also gives me a negative value. So it means that I assume to be going up, and it actually goes down. Okay, so finally I will apply the equations of equilibrium to my third free body diagram. So because now I have these ones and this one, but I will not assume these ones are equals to this one because I took the pin out in both cases. So in this case, I can assume that I left the pin here and I took the pin out here. So I see the same reactions because for action and reaction, I just assume that I took the pin out here and see the reactions from the pin to this bar into that bar, right? So, but here they are asking me to analyze the reactions with the pin and each of the bars. I have this one right here, right? So I have 3 unknowns only. So I will take moment at C to find NA, and then I will add forces and so on. So let me take moment at C, and I have that the Y component, and I have this angle right here, right, which is 45. So, and this is 1. So it's 1 times dB square root of 2 over 2 negative NA, and the distance is 3 equals to 0. Therefore, NA is equals to negative dB, and you know dB we already found is negative 18 square root of 2, and this is square root of 2 over 2, right, divided by 3. And therefore NA, of course, give me 6, right, positive. And that it's important to understand the concept of a normal. That could have not given us a negative number because the normal is supporting that wheel. So the normal force has a known direction that it goes up. So now I add forces in X, and I have that dB plus square root of 2 over 2, right, because I have to decompose the force, plus Cx 2 prime is equal to 0. Therefore, Cx2 prime is equals to negative 18 square root of 2 times square root of 2 over 2, and give me that Cx2 prime is equals to positive 8 kilonewtons. So what I just found, that since I don't have any other components in the X direction in this joint, it means that these two reactions are equal and opposite in direction, which is action and reaction. And finally, I add forces in Y, and that gives me NA, which I already know, dB square root of 2 over 2 plus CY2 prime equals 0. And from here, I solve for CY2 primes. And of course, I plug in all the numbers, and I get that it's 12 kilonewtons. And the same, so here we will say, well, if those two reactions are equal, then I don't have anything in the Y direction. So let's analyze the whole structure, and we'll see that it means that this normal force is equals to 0. Does that make sense? And actually it does make sense, because if you do the free body diagram of the whole and you take moment at A, you will see that that is the external force applied, and this will be the only reaction. This one doesn't create any moment at A, therefore the normal force at C is equals to 0. That's why we got the same values in the opposite direction for the two reactions at the pin at C. So this is the solution of this problem.